Support for Central Florida Public Media comes from the UCF College of Business, offering the new online Space MBA, designed for professionals in innovative and high-growth industries. Beginning spring 2026, students gain advanced business skills through the lens of the space economy. Learn more at business.ucf.edu/spacemba.
Finding signs of life on rocky planets and distant ocean worlds. You're listening to Are We There Yet? The radio show exploring space exploration. Hi, I'm Brendan Byrne. NASA's Perseverance rover is on the search for ancient signs of life on Mars. To do that, it's examining and collecting rocks from the Martian surface. One of those samples have what scientists describe as poppy seed or leopard print-like spots, which could be evidence of past organic life. We'll speak with University of Florida's Amy Williams about the findings. Then, scientists are looking at distant icy moons for other signs of life. On Saturn's moon Enceladus and one of Jupiter's moons, Europa, microbiological life may be under the surface of icy oceans. We'll revisit a conversation with NASA's Alexander Pavlov about his research on these distant ocean worlds. Searching for life in our solar system? That's ahead on Are We There Yet? In the search for signs of life in our solar system, a fleet of rovers is scouring the Martian surface. The most recent arrival, NASA's Perseverance rover, is uncovering potential signs of life and capturing samples of Martian rocks to eventually be sent back to Earth. And before Percy, there was Curiosity, which is celebrating 13 years on the red planet. To talk more about Percy's most recent scientific findings and the baker's dozen of years Curiosity has spent on Mars is Amy Williams. She's an astrobiologist at the University of Florida and scientist on both the Perseverance and Curiosity missions. Amy, welcome back to Are We There Yet?
Thanks so much for having me on.
I was coming across some news stories recently, and there's a very interesting finding, the Sapphire Canyon rock. Tell me a bit about this rock.
So this is a special sample that we collected. We actually collected it last year. So Sapphire Canyon, we have this crazy naming scheme. That is the name of the core that we collected. And that comes from a rock that we named Shiava Falls in this big, basically, river channel, this ancient river channel called Neretva Vallis. And so this rock and this outcrop has become really sort of a focal point for some of the astrobiologists on the mission, because some of the features that we see there, when we see similar things on Earth, those types of features are formed by life. Just because it looks like life doesn't mean it is, but it's those kinds of observations that make us pause and say, what are we looking at? Is it possible that we are seeing evidence for what we're calling a potential biosignature? So that is in contrast with what we would call a definitive biosignature. Dr. Amy Williams is a definitive biosignature, if this is reality and not a computer simulation. But a potential biosignature means that you're looking at something that requires more investigation, because it is intriguing enough that we know sometimes the kinds of things are made by life on Earth. So does that apply to Mars?
And some of these things in the rock, I read they're called poppy seeds and leopard spots, right? Is that the technical term?
Not technical term, but we do like having a term that, like, if I say, someone says poppy seed, you can picture what that looks like, these little dark specks, and leopard spots. So yeah, these are compositional differences in the rock. And so when you get this kind of zoning where you have iron and phosphate, those are elements or compounds that are often associated with life, at least on Earth. And that's part of why this is such an intriguing discovery.
These spots are more microbial, right? This isn't like, they're not etchings in the rock that may have been caused by gases from life or something like that. We're looking at the very, very microscopic level of the rock.
Right, yeah. So you can see it with sort of our hand lens scale imaging system. So you're able to see it at really high resolution. So you wouldn't necessarily need a microscope, but if you were on the ground looking at this yourself, you'd probably want a hand lens or a little magnifying glass to resolve these. So they are quite small, and the thing that we tend to look for is moving under the assumption when you're searching for life beyond Earth. Let's start with something that is single cell and microbial, as opposed to looking for much larger creatures. But yeah, that's part of why this is so intriguing, is that microbes do create these types of what we're calling leopard spots on Earth.
What would make this a definitive biosignature?
Bringing these samples home would be the only definitive way to try to answer that question of whether these features were generated by life in the ancient past on Mars.
What are some of the kind of maybe under-discussed scientific observations these rovers are making on the surface of Mars?
We have instruments on board both of these missions that are able to tell us about the weather on Mars. As we're monitoring over years, we're getting more insight into the climate of Mars. Some of the things that we get to do, other than like weather monitoring things, is you can actually monitor the way that wind is influencing material on the surface of Mars with our missions. And so, recently we did this with Perseverance, but we do this time to time with both missions, where we have what we call any kind of wind sort of formed structure. The technical term is aeolian. And so we have these little aeolian campaigns where we stop at basically dunes or ripples, because you can actually learn quite a bit about the current climate, the way the wind is blowing now, the way the wind has blown in the past. You can learn a lot about like both local and regional geology based on the little tiny grains that are in these sand dunes. Sometimes the dunes don't move and they sit there and they become almost fixed in place, what we call indurated. They get these like hard crusts on them. And we do see things like this, of course, in the terrestrial rock record. We see these what we call fossilized dunes, and you can see them sort of in the American Southwest, preserved in these big exposures where you can see how dunes were kind of climbing on top of each other in these desert environments. And that's one of the things that's really cool to get to explore on Mars, because it's similar processes, which we know are going to happen between Earth and Mars. But you're seeing sort of the most active sort of erosional process on Mars now. There's not glaciers that are moving material anymore. There's no rainfall and a robust water cycle to move material. So it's really the wind blowing over billions of years that moves this material. And by being able to use our instrument suites and sort of study the surface and subsurface of these materials, we can learn more than just about the dunes that are right in front of us, but it shows us sort of a more regional scale of how material is moved around Mars.
You're listening to Are We There Yet? I'm Brendan Byrne. We're speaking with Amy Williams. She's an astrobiologist at the University of Florida and scientist on the Curiosity and Perseverance rovers. Amy, we were just talking about that kind of wind data and all of that. I'm wondering if not only does that help you uncover how geology is kind of shaped by these atmospheric environments, but does it help you rule out other things?
There's kind of two directions to go with this. So one is sort of the weird things you might see. So sometimes you see features like in the rock that are sculpted in these really intricate ways. And it's actually something that we do see in desert environments where wind plays a major role in sort of the erosion of rocks. It creates features called ventifacts. So these are rocks that have been like winnowed away by small grains pelting against them from the wind blowing really hard, and sort of polishing, but also kind of shaping the exposures of the rocks. And so sometimes you see these really cool pictures on Mars where like there's like these little spires and things. It's just wind erosion forming in these dry, cold deserts. It's really cool. So you get cool and interesting and sometimes weird looking structures that form from that natural erosion. And one of the other things with like our environmental and atmospheric monitoring is that you get more information about basically how air moves on Mars. There's actually like sort of this like lower boundary layer. It has to do with, now I'm not an atmospheric scientist, so don't quote me on all this, but it has to do with, let's see, density and how quickly the air is heating up in the morning, how cold it gets at night. And it actually plays a big role, we think, in sort of moving around methane on Mars, which is something that we talk about every once in a while. So there's this like boundary layer that changes every day as the sun comes up and sets, and actually moves air around pretty quickly in Gale Crater. So that is, a geologist's take on what's happening with the atmospheric stuff, but it's not something that we necessarily initially expected on Mars. And so over careful data collection, modeling, and interpretation of our results, we've come to these conclusions, which were not necessarily things we expected.
I want to talk about Curiosity because it did celebrate a milestone, 13 years exploring the surface of Mars. And my understanding is you have long been connected with this mission. Do you want to reflect on 13 years of Curiosity?
I'm sure I've mentioned it to your listeners before, but that mission is why I am a Mars astrobiologist. I joined the Curiosity mission when I was a graduate graduate student at the University of California, Davis. I actually joined the mission before it launched. And so I had the opportunity to participate in the final landing site selection meetings, to go to the launch at the Cape, having no idea, of course, that I would eventually end up at the University of Florida. And then about 9 months later, you have entry, descent, and landing. And remember that Curiosity was the first time that we used the Sky Crane landing system.
It's bonkers.
I mean, this ridiculous rocket pack on the back of our rover.
And it worked.
It's bonkers. And no one knew it was going to work, right? And so I remember having a watch party at UC Davis, because I didn't go down to JPL to work on the mission until a few weeks after landing, because a lot of it is commissioning and stuff like that. So we had this watch party on campus, and I remember sitting there thinking, if this thing crashes, I don't know what I'm going to do my graduate degree on. And so many people, students, professionals, engineers, scientists, we were all having that feeling at the same time. And people throughout sort of like our space exploration era, decades that NASA and other space agencies have been doing this. We all kind of have that same feeling when you're watching, EDL, and you're like, please land, please work.
And it did. What do you think the coolest finding by Curiosity is so far in its 13 years of operation?
Without maybe being biased towards the organic chemistry part, which we know I really enjoy, I would say landing, and within a few months of landing with Curiosity, accomplishing our primary goal, which was to characterize a habitable environment, a place where microbial life would have wanted to live in the deep past. And we actually happened to land, within just a short enough distance of this ancient lake bed at the base of Mount Sharp. And it ended up paradigm shifting in a way in which we're finally able to characterize these environments, to understand life would have wanted to live there, and start to set the stage to understand that there are all of these habitable environments on Mars where life would have wanted to live. It's like looking back and realizing that was so important and you felt it then, but then seeing the scope of it now, you're like, that really set the stage. That got us started on this new era of robotic rover exploration.
Finally, Amy, you mentioned the kind of the lessons that we've learned from Curiosity are paradigm shifting, and now we're seeing that NASA is facing historical funding cuts. What is on your mind when you think about the future of these exploration initiatives, when funding could very well be diminished?
More than diminished, completely gone. It's full careers thrown away. What I do want to say is it's not just science because it's nerdy and cool and we want to learn about it, right? The work that scientists and engineers are doing on planetary missions serves all of society, all of humanity. We're able to create new technologies that help people. We're able to expand our understanding of ourselves and our place in the universe, our ability to be good stewards of our one and only planet. It's really been heartbreaking for me as a scientist, as a human, to watch the funding cuts come through. They're certainly impacting my ability to do my work, and they're impacting the ability of the students in my department to get jobs in the fields that they've trained for. It's really heartbreaking to watch it happen and unfold in real time, and I feel rather powerless, except for these opportunities to speak with people and explain to them why what we're doing is important, and to ask for people to show support for the science and technology and engineering that does make our lives better on Earth as well as in our exploration of other worlds.
And I appreciate you making the time to bring that to us each and every month here on the show. Amy Williams is an astrobiologist at the University of Florida. She's a mission scientist on Curiosity and Perseverance. She's also a definitive biosignature. Amy Williams, thanks so much for joining us.
Thank you.
Still to come, Mars isn't the only place scientists are searching for life.
So essentially you have two ocean worlds. Life as we know it require liquid water. So that in itself, by itself, make those moons a prime target for life search.
The search for life on icy moons. That's ahead on Are We There Yet?
Support for Central Florida Public Media comes from Daytona Beach International Airport, offering new nonstop service to New York City and Boston, Massachusetts, beginning December 4th. Daytona Beach International Airport features convenient access to the terminal, easy and close parking, and more. Details at flydab.com.
You're listening to Are We There Yet? I'm Brendan Byrne. Farther away from Mars in our solar system, there are two freezing moons with vast oceans beneath their surface. On Saturn's moon Enceladus and Jupiter's moon Europa, scientists think that amino acids may exist beneath their surface. NASA Goddard Space Flight Center's Alexander Pavlov led a research paper about these moons, saying that microbiological life could exist, but to uncover that evidence, future missions would need to drill through the icy surfaces to see that life. We first spoke with Pavlov last year about these icy worlds and the possibility of life. Here's that conversation now. Well, Alexander, thanks for joining us.
Thank you for this opportunity.
Well, Alexander, let's start by talking about Europa and Enceladus. These are two moons that are quite far away from Earth, and there might be oceans beneath their surface. But specifically these two moons, why are you looking at them for possible signs of life?
As you said, there might be oceans. It's not might be. We are confident there are. Yeah, so for this particular moons. On Enceladus, we actually see the liquid water shooting from the South Pole. On Europa, there were evidence for the plumes shooting water out, but it's much more sporadic. But from the magnetic field measurements, we know that there have to be a liquid ocean right underneath the ice on Europa as well. So essentially, you have two ocean worlds. Life, as we know it, require liquid water. So that in itself, by itself, make those moons a prime target for life search.
You describe these environments in a way that sounds quite inhospitable, right? They're icy. They've got these plumes that spew out of there. Is this kind of an extreme environment within our solar system? And how might there be life in an area that spews these water geysers out of it every so often and is frozen?
Well, it's inhospitable in our view at the surface, but not under the ice. I mean, we have plenty of life in Antarctica under glacial lakes. There is life deep in the ocean, which have barely any light whatsoever. So it's not. If you sit on the surface in life as we know it, will have troubles. But once you go deep in the ocean, under the ice shell, there's plenty of terrestrial microorganisms which can handle it.
Up until this point, Alexander, how have planetary scientists like yourself made these observations on Europa and Enceladus? How are you so sure that there is water there, and how are you able to paint a portrait of what this environment looks like from all the way here on Earth?
Well, telescopes, they do the job. The most recent was amazing images by James Webb telescope looked at actually at that shooting plume from Enceladus. That's directly. But even before that, there were observations of similar type, where you actually see this icy. Well, the liquid water immediately become ice as it shoots up. Then there were measurements of organic molecules by Cassini instrument, which has mass spec in the E-ring of the Saturn, which we think now is being feeding from these plumes from Enceladus, and you see organic molecules in there. So then you look also before we had observation, people were looking also at the surface of, say, Europa, and they are looking at particular features on the surface like tiger stripes, and they were looking at how they can be formed, by cracking the ice, liquid water coming in, then crack again and again and again. So there's a fairly mature body of evidence. People are debating how thick is the shell on both planets, but again, from the magnetic field observations of Europa, you can tell that there have to be a liquid conduit underneath the ice with ions in it. When it's moving, it's producing specific magnetic field. This is another type of estimates which scientists use. Even though we directly didn't drill, well, hopefully we'll drill at some point, but not anytime soon. But there's a way how you can tell remotely that there should be massive oceans underneath those shells on those icy moons.
So you mentioned you're using telescopes for remote observation, but also getting data from Cassini, the spacecraft that was living around Saturn for quite a few years and taking observations. But obviously, you want to get there and you want to crack that shell, right? Tell me a bit about what a mission like that would look like for both Europa and Enceladus to actually get something, air quotes, on the ground, looking at what is beneath that surface.
Well, the biggest challenge for Europa is the obviously radiation environment there. As I said, when we are thinking about inhospitable environment for life, it's not so much temperature. So we worry about radiation. This is what our paper is also about. On the surface of Europa, it's in the radiation belt of Jupiter, and fluxes of these ionizing radiations are tremendous. So it's very difficult for equipment would be. So that's a challenge. On Enceladus, it's far away. So it's a major investment to get even there. But in my opinion, based on our studies, we're well worth the risk, because on Enceladus, you can preserve the science of life on the surface where you can sample it. Obviously, drilling is a very energy consuming and therefore energy very expensive enterprise. What you're going to do in any of those missions. So if you don't have to drill and you still can collect valuable information, that's a major boost, for the mission. So that's what our paper was about. We discovered essentially that on Enceladus you don't have to dig at all. The biomolecules will preserve essentially right under the surface. And even on Europa, even though it's hotter there are locations where those molecules can be preserved. We're fairly close to the surface. So Europa is hotter, but still doable.
Tell me a bit about some of the findings in the paper. What do you hypothesize that is allowing those molecules to be preserved at the surface?
When we're looking at life, we're not looking at the actual living, moving organisms. Our approach is kind of based off life, what we know it is that they all have to use the amino acids. We were basically asking ourselves if life is present on those moons, how long the biomolecules, which we think with this life will be made of, would be able to preserve on the surface. How long does it take? And at what depth we will have a significant fraction of these molecules relatively intact, relatively not affected by radiation. So that was the point of the study. But the approach itself was life as we know it, all made out of nucleic acids, amino acids, kind of a very specific set of biomolecules. So we don't obviously know exactly what would be alien life made of, but if it's organic based, it's logical to assume that something similar molecules. So if we find the kind of depth or environments where they can be preserved, that's good for the life detection.
And is there a sense that if you are able to find those amino acids, those kind of building blocks on the surface, that could mean that there is something more complex beneath the surface?
Yeah, so amino acids by themselves can be fairly complex molecules. There are small amino acids that are more complicated. But what was more special about amino acids in particular is that they have a chirality. It's left-handedness and right-handedness. It's a type of orientation of the molecule itself. And all life as we know it is made out of left-handed amino acids. We are not taking any right-handed amino acids in any cells, whether it's human body or E. coli bacteria, or elephant or bird. They're all utilizing left-handed amino acids. And in nature, the proportions are much more even, left-handed and right-handed, like say in meteorites. So imagine you arrived on the surface of Europa or Enceladus and find these amino acids, and they all are either left-handed or they're all right-handed. That would be a pretty darn big indication that that's actually biosignature.
And how soon might we be able to confirm something like that? Alexander, I know that there's a lot that needs to go into that, and essentially you'd have to send something out there. But I mean, are we talking in our lifetime that you'll be able to get the answer to that question?
That's part of the rationale for the study, is to show that such missions, they don't require drilling. And if you don't require drilling, well, maybe that prompted to that is not as expensive as it would be. Our job is to put NASA in best position to make this decision to go there and to motivate. So this is what the paper is about. And currently there are no missions planned to go and sample. Yes, it is my hope that during our lifetime we'll be able to do it. Yeah.
Yeah, it can't be too difficult to send something to go sample out there, right? Super cheap and super easy. Alexander, your focus on this paper and your current planetary research now is on Europa and Enceladus, but your main background is on Mars, which is a much different environment than these two moons. Can you tell me a bit about how you transitioned from Mars to places like Europa and Enceladus?
Well, my interest is in finding life in our solar system, right? Whether it's past life or current life. And on Mars, you're right, it's planet mystery from all standpoint, but the current missions are mostly focused on the finding evidence of past life, because back in the past, Mars was warm and wet. It's dry right now, and there are still locations where you have liquid briny water present, but mostly it's a dry planet with just ice in the polar regions. In contrast, right now, if you're interested in something which is living right now, both icy moons, they have entire ocean liquid. Obviously, that makes it a primary interest for astrobiology. So I'm not limiting myself to one planet, even though Mars will be my first love at all times. But the Enceladus and Europa, they're very, very tempting targets.
Finally, Alexander, I ask you this question knowing it is very speculative, but for planetary scientists like yourself who are on the hunt for life in the universe, I do like to ask this question, and that is, where is the best chance for us to find that evidence? And how soon might scientists like yourself find the answer to, are we alone?
There is several questions in that question, right? In terms of where best find and how soon we find might be not, they're two different questions. In terms of how soon, probably we will have the best chance. If life is there, we'll find it on Mars. This is a life search missions probably in a decade from now. Missions in the planning right now, like Mars Life Explorer, and it's nothing certain yet, about those, But in terms of best chance for life to be, that's probably icy moons. They're much further away, and that the mission will take longer in planning and execution. But that's the best chance of actually finding. But we will be able to have a life search mission before that to Mars.
Well, I'm fascinated by your research and appreciate you sharing it with us. Alexander Pavlov is a planetary scientist at NASA's Goddard Space Flight Center on the hunt for signs of life in our solar system. Alexander, thanks so much for joining us.
Thank you.
That was NASA Goddard Space Flight Center's Alexander Pavlov. The conversation first aired in July 2024. That's going to do it for this week's show. If you're not already, be sure to subscribe to the show's podcast feed so you never miss an episode. You can do that on the Central Florida Public Media app, Apple Podcasts, or Spotify, or really wherever you get your podcasts. Stay connected with the show. Follow us on social media. We're on Instagram and Facebook. We're at AWTY Space. If you've got an idea for a future episode of the show, or you want to join us as a guest, reach out to us. Our email is arewethereyet@cfpublic.org. Are We There Yet is a production of Central Florida Public Media. Our intern is Orion Boone. Our producer is Marion Summerall. And editorial guidance comes from LaToya Dennis. Support for Are We There Yet comes from our listeners. Until next week, I'm Brendan Byrne. Thanks for listening.